that's the edge enhanced mode. There's another mode I have here called level slice. I'm going to show you that. Okay, now I should point out here we're looking at a Cosmo Skynet image right there. You can see CSK, satellite 1. So this data is in the original raw format as from the data supplier, and we're looking, single look slant range. Anyhow, this level slice, what it does, okay, and this is a real-time tool that I put together for our Federal Emergency Mapping Agency. So and here's the reason, right? They came to me after this New Orleans flood, and right, we all know about the New Orleans flood. And so the question was, can you give us a tool that'll allow us to quickly map floods? And we don't know anything about radar, and right, we never will be radar experts. But this is all real stuff, right? Optical data is not going to do any good because it's cloudy. Got to be a quick response time. Where the flood was yesterday is totally irrelevant. And this final thing is, it's got to be something that first responders can read, right? These are policemen and firemen and ambulance drivers. These are not remote sensing experts. Okay, so there's the radar scene I had. This is a real flood. This one happened. Okay? So I can zoom in. I can move my threshold here and very precisely draw the line between what I want to call water and not water. And it's not really water. It's really just specular reflection. Okay, so I'm not really measuring water. It's kind of indirect, but it works. The point is, and then the final step was when I'm happy with my old threshold, I push the last button, which is raster to vector, and I make a shapefile. Shapefile is concentrated information. I can stick that in an email and send it to somebody and download it on their little Palm Pilot, and we're in business here. So this was a real project. Like I said, this was a flood. In fact, this is one of my favorite little stories because I was actually in a hotel in Amsterdam. They called me on Saturday morning and said, "We got a flood in Colorado." So I FTP'd me the data, right? Played with my button a little bit, sent them the shapefile back, and when the guys in Denver got out of bed, they had their maps. Okay, this is real-time stuff. But there's a couple points I brought in here in the sense of actionable information. You can, of course, looking in here, you may find places where there's a lot of water that could be blocking the roads. Okay, if you need to get supplies through there, ambulances, whatever, you obviously know where to send somebody to find out is the road open or not open. It's actionable information. But another one interesting one I found was here. I see a lot of flooding around this building right here. Now, like I said, I have a shapefile, so I can put it on top of anything I want. So I put it on top of a base map that they sent me. This is a correctional facility, right? That's a prison. Okay, that's the same category if it was a hospital or a school or anything. It's an infrastructure we need to keep an eye on. So obviously you just make a phone call. Is everything there? We see some flooding in your area. Your generator's okay. If you have any problems, here's the phone number, right? Actionable information. Otherwise, these guys sitting in the command post, how do they know where to send people? How do they know where the emergencies might be, right? This is actionable information for them, unquestionably. And there's the same shapefile put on top of optical images. So that's the point with the shapefile. It's easily transferred information. And these are the kind of products that we make during these floods. You see, it's actually, in the States, it's the Air Force that does this. That's the United States Air Force Eagle Vision that has this responsibility because they have a mobile receiving station. So they can get this data downloaded instantly. And you can see what we make here. These are all red flood vectors on top of a standard quad map. Everybody understands standard quad maps, so they're comfortable with it. It's not this weird radar thing that they don't understand. And they were justifying their work. But the important point is this number 4 here, right? The storm was still going on. We can do this stuff while it's still cloudy and rainy. There's no optical competition for this one. Okay, that's the radar analyst workstation where we work on the magnitude. And there's some other tools, of course. It's growing all the time. Well, let's talk about interferometry. That's where we work on the phase. I've been in image processing all my life. Okay, I've done wavelengths, I've done Fourier transforms, I've done principal components, I've done all this stuff. Interferometry is more complicated than all that stuff. It's the most complicated image processing stuff we do. One simple example, when we started doing interferometry, we had to start doing all our calculations in double floating point instead of single floating point. Just have enough decimal places to carry the precision through, right? Stuff like that. So it's very sophisticated. You can't look at it, and we have to kind of do this stuff automatically. And within this package, we have coherence change detection, this time series coherence change detection, and then DEM calculations and subsidence calculations. Okay, these are just some of the basic designs of this interferometry. Here, the red arrow says we're on the input step. So each one of these steps has its own little GUI with a couple parameters you might want to change. Not enough to kill yourself, but a little bit. You can see here we ingest the data in native format. We're not doing this import stuff. And ingesting is not just the pixel values. It's all the metadata that you need to do all these different sorts of steps. Okay. Again, I'm focused on production, not a toolkit. So the things I've been talking about, the radar analyst workstation, the interferometry wizard workflows, this is not a toolkit. It has all the same tools as the toolkit, but they're put together in a logical, scientifically defined processing regimen to kind of walk you through this stuff step by step. It's not a research tool for graduate students. So within that context, these are kind of like my rules in life, is that every variable has to have an intelligent default. I have to assume that whoever's doing this has no clue, and that they'll get a pretty good answer. So, to give you an example, however, like this chip size or template size, whatever you want to call it, 64 by 64 pixels. That ends up being the best value probably 75% of the time. Well, that's a lot, so that's the obvious default, but it also means 25% of the time it's not the best value, right? So there's a drop-down list here. There's half a dozen choices, 32, 128, like that. And also, when the process runs, it dumps information in this thing we call the session log. I can't go into that a whole lot, but it's part of the software just tells you various processing parameters. So you can go through and change this, try 2 or 3 or 4 different chip sizes, look at the session log, and kind of make an intelligent decision. So the software has enough flexibility to allow you to refine it if you need to, but not so much flexibility that you can just do crazy stuff that's a waste of time and it's not creating information. Sorry to have to go so fast. This is another one of my cardinal rules. I have to team with other people. This stuff is so sophisticated and so complicated, there is no group that specializes in every one of these steps. Okay, it's certainly not me. So for example, within our interferometry package here, co-registration, I partnered with a group in the States called Vexel Radar. You know Vexel. They did that with us. Spectral shift filter was developed working with a team at the German Space Agency. And the unwrap algorithm also came from another team at the German Space Agency. This is the unwrap algorithm that was used for the SRTM mission. Okay, the DEM, are we going to download the SRTM, that shuttle radar topographic mapping mission? That was an interferometric mission. So this algorithm was developed for that mission by the guys at the German Space Agency. They told me it took them 10 man years, 1 million euros, just for that one step. And it's been tested with, I guess, 13,000 image pairs. So this unwrap algorithm is serious. And it needs to be. Unwrap is like the motor in the race car, okay? You buy a race car, that's $1 million, engine's another $1 million. Whoever has the best engine wins the race, okay? Well, that's how unwrap is the engine for interferometry. And the final thing here is that I'm focused on information products, okay? And this is a good example of it. We're looking here at the CCD wizard workflow. You see it's a little simpler than the INSAR and DINSAR. You see it's a CCD project, but you notice all these wizards are pretty similar, right? So once you can do CCD, do an INSAR, DINSAR, it's just a couple of more steps. It's all as similar as possible. What I'm pointing out here is that in this world of coherence change detection, CCD, I'm going way beyond grayscale images, okay? I showed you that grayscale CCD image where I inverted the contrast on it, right? It's nice, there's a lot of information there, but it still has the same grayscale problem, okay? So there are several color composites that are becoming accepted in the industry as something we all kind of like. And so there's a bit of a push between me and several folks like Telespazio to try and have everybody standardize on these things. Because again, remember, what's the thing? We've got to pass information to that guy who has to make a decision. So we want him to eventually say, oh, I know an IOU image. I need to look for the red things in an IOU image. The blue stuff I don't really care about, and green, okay. Just like, if you say, I have a color infrared. People know color infrared's a standard product, right? We're trying to do that in the world of radar, So we start having standard information products. Right? That's where we got to get to. We got to do, you know, like I say, we're working together. So let's talk about CCD. CCD is real important stuff. Real important stuff. I was at a facility out in Colorado. They told me they make CCD images faster than McDonald's makes hamburgers. Okay? So we're talking about people getting stuff done. We're going to use those same two images that we played with before, the Panama Canal, that single complex stuff that I like so much. The last time we looked at the magnitude, right? We took that magnitude layer, put it in the radar analyst workstation, did all these little tricks to enhance it. Well, let's do the same game with the phase, right? And that's a big pile of radar data, right? Suddenly you can extract all this information out of the magnitude, and then you go to the phase and extract more information. It's more information rich than optical scenes. It's a little bit harder to get it out, but we're making it easy. Okay, there's our same two gray friends. Again, trying to find change between these two images is a, you know, I wouldn't want the job, I'd rather plow a field. Okay, there's your standard coherence image. Okay, bright means no change, dark means a change. Okay, a bunch of infrastructure, buildings, you know, port stuff, and the jungle. That makes a lot of sense, but again, gray is not the most amount of fun to look at. So these are the other products that you can make, right? This is called interferometric land use. Okay, remember I've got these two images, I co-registered them. I'm doing the phase change, so I might as well do the magnitude change at the same time. Okay, so what I've done here is I've taken my coherence image, which is a change in phase, took my two amplitude images, got the change between the two amplitude images, and then for the third band I just averaged them together to get a nice, you know, low noise base layer. And it forms, right, a color composite with, you know, color-coded information. Here's another one, multi-temporal coherence. The guys at EGOS love this one. This is like the product for Cosmos SkyMed. I was at their building. 2/3 of the pictures on their walls are multi-temporal coherence. Again, it's fairly simple. I have two images, right, before and after. So I can make my coherence layer, that's the C, and multi-temporal is just the two images, right? I have two images taken at different times, right? So multi-temporal coherence, just stack them up. Again, color-coded information. Easier for the analyst, easier for the decision maker who doesn't even like radar data, right? And here's sort of the latest kid on the block. It's called coherence texture. I call it coherence texture. Some people call it COVAMCO. You might have seen it under that word, COVAMCO transform. The concept is just that one of the layers we put in here is a quantification of texture. Radar is real sensitive to texture. So we might as well get that information in there. So when I run CCD, right, I don't just make this grayscale thing, I make all four of these, okay? And then I just sit and look at them in the viewer. Because sometimes one color composite brings something out that you hadn't noticed before, and then you go back to the other layers, you go, yeah, it is kind of there, I hadn't really noticed it before. And eventually, you go all the way back to your original images, right? You're really making a serious decision, but all that stuff's in the workstation. So these are CCD products way beyond the standard grayscale thing. Okay, like I said, time series is real important. So we've got this tool for these people that make them faster than hamburgers. And they're, of course, monitoring certain facilities on a routine basis, every 2 weeks, every month, whatever, you know. We've been talking to, you know, the guys at Telespazio about some 24-hour experiments. But the point is, you throw a bunch of images in here, it automatically puts in a date sequence. If I had another image, it would add it on the bottom, hopefully, unless I had the wrong date, you'd have to reorder them. But the point is, I can slowly build up my project. I save this as a project file, new scene comes in for my area of interest, I bring in my project file and just stick the next image into it, okay? And you can see it's got 3 tabs. We'll look at the input, and we'll look at workflow and display. Now this thing here where I can edit a template, load a template, the template is where I tell what I want it to make, right? Like I just showed you, I can make a coherence image, I can make the ILU, the MTC, coherence texture. What do I want to make? Well, I just tell the template what I want to make. Now here everything is green, that means they've all been calculated. If I added another image, then I'd have, right, 4 little red things here until I hit OK and it did the calculation. So this just does my homework and tells me the calculations are done. And then I come to this one here. Now you can see there's all these products I can make, and there's also the option to throw a filter on top of this thing. So I could, in theory, create 8 different products automatically with this coherence, not just this grayscale image. And then I would push, okay, display in the viewer. I want to see this stuff. Why? Okay, here's a good example. We're looking here at the ILU, the interferometric land use. where I did the magnitude change, the phase change, and the average. And we're looking at a pretty important area here. This is the border between Egypt and Israel and Gaza Strip area. A lot of people monitoring it. I created all these images, I pushed the viewer, and it stacks them all into the viewer, right? So I've now got 4 or 5 color-coded change detection images in a time sequence in my viewer. And there's a couple buttons I can push that goes through this stuff, but you know. Okay? You can see why they call it interferometry land use, right? You see this stuff changing. But the point is, in an operational context, I would have to zoom in, and I would go through this frame by frame. But while I'm moving through my image frame by frame, at each frame when I stop, I'm going to go through this whole stack, okay? So I can go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, oh, what was that? Okay? And I put one here to show you the kind of stuff I'm talking about. Right? You notice that something suddenly occurs in this one time period, right on this border spot. Well, as you know, there's people digging tunnels and all sorts of stuff around this border. So that is actionable information, right? Somebody, you're going to get the latitude and longitude, and someone's going to go with binoculars and a camera and explain exactly what's going on here. But now let's go back. You have 7 grayscale images, like I've been showing you, and you're going to find that by going through them. Never going to happen, okay? That's what these tools are designed for. Uh-oh, copyright time. I'm going to go quick now. For one thing, the DEM stuff is so fast. We'll take 2 radar images, and we're going to process the phase. Now let me mention, when you use these wizard workflows, it's set up so when you have to make a decision, like a ground control point or a tie point or something, I show you the magnitude wave. 0.5 centimeter, blue is 0.5 centimeter. Okay, now we're down in the millimeter world. That's how, you know, there's no optical equivalence for this kind of stuff. This is serious precision. But this is an example of a DEM I made. And one thing, this is Arizona, not a lot of vegetation, so I don't have this problem, vegetation decorrelation. That just kills interferometry, vegetation. Yeah, it kills it. But the point is here, when it works really nice. And this slide here, and actually a lot of my slides, I purposely just take the defaults. Because my purpose is not to show you the best scene I can make. I've been doing it for 30 years. I want to show you what the software can make for you automatically. So my nephew can do this, right? You just input the images and push the button. And if you're used to looking at DEMs, you can see this outwash playing out here. This is a very high resolution DEM. Just to prove the point here, I'm comparing it, there's the SRTM DEM that you download from the internet over there, right? The 30-meter DEM, which is good. That's a DTED level 2, right? 20 years ago, that DEM was worth a fortune. It was worth enough to fly the space shuttle for 2 weeks. But look at the DEM next to it that I made automatically, just taking the defaults, right? Probably close to DTED level 4. When it works, it works. Subsidence is very similar stuff. I won't go into it a whole lot. The stuff we have implemented for subsidence is what we call 2 images plus a DEM. It's the simplest way to do subsidence method. There's much more sophisticated techniques that use a lot of images, right? Persistent scatterers, small baseline analysis. Very interesting stuff. I've been working on trying to get this commercialized. It ain't easy. These are very, very complicated processes. So what I've got in here is what we call 2 images and a DEM. Again, same kind of friendly little wizard workflow. You recognize most of this kind of stuff. You only have to make one decision to use this software. You have to give me a 0 reference point, right? Everything's relative, right? Give me a spot that didn't do anything, and everything else is calculated relative to it. And you can see, you have these little check boxes to convert it into vertical and horizontal motion. It's just geometric calculations. But this was a fun one because this was a little pilot project. I work on a lot of pilot projects because, right, remember I told you, just because it's a pretty colored image doesn't mean it's information. So I have the responsibility to actually quantify this stuff and prove that it's real. So this was an important data set for me. This was an NVSAT time series. Okay, NVSAT C-band, very similar as we just talked about the Sentinel-1. This was a time series analysis. I think it was about 30 images. The processing was done with Gamma software, which is extremely high quality software. The problem was that information right there costs over $10,000, okay? And these people have over 50 of these sites and they want to monitor them twice a year. So it's not cost effective. So they came and said, what can you give us that'll get us a nice answer quick and dirty? So pay attention here. You know, here's my subsidence feature, right? This blue and green thing coming around here. Dark is where I lost coherence, right? There's a town here, a river, some ag down here. But you can see kind of the shape of this feature, subsidence feature. And I can tell you some stories about that, but we're going to run out of time. But you know, everybody's been kind of modeling subsidence as like a bowl, okay? It's not a bowl. So there's a lot of ramifications there, serious ramifications. Anyhow, this is what I can get automatically using 2 images and a DEM, okay? And if you look, right, you can see this, I got exactly the same sinuous feature, okay? It's there. And what's nice about it is if you look, my coherence is actually fairly low in this area. So even with, you know, fairly low coherence, I get a very nice answer. The problem is, of course, in the reality, the mountains didn't rise up. Those are probably errors in my DEM, possibly errors in the baseline. All this modeled stuff up here, that's probably differences in the atmosphere between the 2 images. So I've got a lot of false positives in there. And I can't go into it right now, but you know, you get 1 phase position, right, for every pixel. But there's a bunch of components in that, right? There's the system noise, errors in your perpendicular baseline, changes in the atmosphere, differences in the DEM. So there's about 6 different components that give me this 1 phase effect. So it's hard to separate that out. And that's why people do this time series analysis, right? The theory is if you've got 40 or 50 scenes, you can kind of suppress the atmosphere, right? You can kind of start standardizing your DEM error. You can start making estimates on your perpendicular baseline, because some of these kind of random errors start averaging out with 30, 40, or 50 images. But before Sentinel-1, that was just not feasible for very many people. Really just what we call the mega fields. In Saudi Arabia and Kuwait was the only place that could afford this kind of technology. So Sentinel-1 brings up some interesting options there. But my point here is the reason I have a little cursor here is this is quantitative information. This is not just a dark pixel. Every pixel is encoded in the change in millimeters. So I can put my cursor right here and say that pixel subsided 25.4 centimeters. Right? It's quantified information. And of course, you know, we had people in the field with differential GPS and stuff like that, so we could check out and make sure this was all happening correctly. And I published this in GeoWorld, and I've started publishing a lot of my stuff in these what we call trade journals instead of IEEE transactions and all these kind of science things for this exact same reason I started talking about. Operational information, okay? I want people to know that in the world of radar, we can extract information that you never even dreamed of, right? I've been telling a lot of people, you need to show your boss this because your boss doesn't know you can even do this. So he's never going to request it. Radar data is not a substitute for optical data. If you can do it with optical data, do it. It's cheap, we all know how to do it, we all understand it. Use radar for the things it does that has no competition. That's where the strength is at. That's it.